Okay, thank you guys for coming. So I'm Alfred. I'm a solution consultant here in Sahaj. So am I audible in the last one? Cool. So this talk is about Spark. So how many of you are familiar with Spark or used Spark in your work? Okay, and which versions of Spark have you used? 2.3. Okay, and for what? For batch processing or for streaming?
For recommendation system.
So for ML, right? Okay, that's good. So this talk is all about my learnings with Spark 2.0 and how we are using Spark and how to develop Spark applications locally. And so to take that application that you've developed locally and then like run it in the cloud. So that is what this talk is all about. And so this is an introductory talk. So we'll start from the basics of what a data processing framework does and how Spark is different from the other frameworks. So this is the overview of the talk. So we'll start by discussing about the data processing frameworks and Spark's architecture, and we'll briefly go through the differences between Spark 1.x and Spark 2.x and what's new in Spark 2. And then we'll look at some of the things that, some of the concepts in Spark and how Spark works under the hood. And like I said, we'll see some demos of developing a Spark application. And then finally, we'll look at how we can run a Spark cluster in AWS. Okay. So let's talk about processing data. So I want to start with this question. So sorting is a very common data processing operation. And so let's say you have 100 gigabytes of data and you want to sort it. And the constraints are you have to do it on a single machine. And so this is the spec of that machine. And let's say I mean, you can say that all the 10 GB of the RAM is available to you, and all of the 500 GB is available. So there is no other process or any operating system competing for it. So my first question is this even possible? Can you sort this 100 GB of data set on a single machine with this spec? And if so, how? Okay. So how would you do it?
So maybe we can jump the data in 2 GB, 1 GB or whatever it is. We'll sort all those and write it into this. Now we have those number of chunks.
Yeah.
All chunks are sorted.
Correct.
So from all of the chunks, whichever is smaller, we'll take it one by one and write it in file.
But then the final output, right? If you're going to write it like that, so that won't be in the correct order, right? So you need to somehow merge it, right? So yeah, I mean, you're correct. So the reason why I wanted to start with this question was because your normal in-memory sorting algorithms will not work for this problem because you can't fit this 100 GB of data in your memory, right? So you have to somehow split it and so that you can accommodate that chunk in your memory, sort it, and like you said, write that chunk to the file. And so you would, let's say you have 100 GB and a RAM is 10 GB. So if you split it into chunks of 10 GB, you would end up with 10 such chunks of sorted data. Now, the problem is not yet over, right? So we've just sorted these chunks. So we still have one more problem left. We have to somehow combine these chunks into the final sorted output, right? So again, the constraint is you have 10 GB of RAM and each of these chunks are 10 GB, right? So what we can do is, it's like the k-ways merge sort. So we can split the RAM into, let's say if we have 10 chunks, we can split it into 10 partitions. And so each partition will be 1 GB because the entire RAM is 10 GB. If you split it, we'll have 1 GB. And then you have to write a program that will read 1 GB from each of these chunks, keep it in memory, and then perform a merge, right? And then keep appending it to the final output file. And so if any of these chunks is fully read or fully processed, then you can read another 1 GB from this chunk, and you have to keep doing this. So you have to write a program that will do all these operations. So your normal in-memory sort becomes so much complicated that you have to take care of so many things. So this is just a very simple problem. And let's say if our data set is much more bigger that it cannot fit on a single machine, then what would you do? So this again won't work, right? Because now that you could fit this whole data set on your machine, you can split it up into chunks and you can process it this way. But what if the data set cannot fit on a single machine, right? So that is the problem that, like I said, that is one problem. And the other problem is even if you manage to fit it on a single machine by somehow vertically scaling it, adding more hard drives, right? It can take a very long time. So these are some of the limitations if you were to process it on a single machine, even if you vertically scale it. And also you can't do it like after a limit. So these two are the main limitations that basically leads to some other technique that we have to use to process this data. And I think by now it might be very obvious to you. So we are going to, or we are getting to the distributed processing. The reason why we need to process this in a distributed manner. And so that's where all these frameworks come in. So you have so many frameworks for distributed computing, right? You have Hadoop, you have Apache Spark, and you have the latest one, Flink. So yeah, and so like I said, these are distributed computing frameworks. And so some of the main functionalities they provide you are, they'll basically help you partition your data across a cluster of nodes. So if it cannot fit on a single machine, right? So with the help of this, with the help of these frameworks, you can basically partition this data and then store it on a cluster of nodes, and also process these chunks in parallel so that you can finish processing them very quickly, right? Unlike your single node processing, you can process this parallelly and you can get done with it like quickly. And the next important thing is fault tolerance. Since now we are distributing it across our cluster, right? So what if one of your node goes down, and what if you lose that chunk of data, right? So that problem is there. And again, if we were to write a framework to handle all of that, then we just can't get done with this framework, and so that's really difficult. So these frameworks take care of all of that so that we can focus on building our applications. So firstly, I want to talk about Hadoop. So Hadoop was the first such open sourced frameworks for distributed computing. At its core, Hadoop has the Hadoop file system, HDFS, which helps you partition your data and then like store it across a cluster of nodes. And then for processing it, Hadoop uses the MapReduce programming model, as you all know, which is basically focused on batch processing. And but there are other tools to basically facilitate stream processing and using SQL for querying the data. But at the core, Hadoop only has HDFS and your MapReduce programming model. Other things are all like various other tools that can integrate with Hadoop and we can use. But the problem with Hadoop is, even though it really worked, and so it was slow in a lot of ways, and the APIs, the MapReduce programming model was very restrictive, and so Spark was created. So Spark was created to address some of these limitations in Hadoop, and also to support stream processing. And if you look at Spark, the main reason why you would choose Spark over Hadoop is the speed of computation. So I'm not going to talk a lot about that. You can look that up on their websites. So it is extremely fast, and so yeah, let's look at the architecture of Spark. Since it is a distributed computing framework, right? we have a cluster of nodes. So as you can see on the far right corner, so these are the worker nodes that will be there in the cluster, and this is where your data will exist. All the partitions of your data will exist, and these nodes are going to process the data, right? And so since you have the worker nodes, you need a master node to take care of all. I mean, you need a master node to basically coordinate with all the worker nodes and assign work to them and all of that. So that is why that is the responsibility of the master node. And we have the cluster manager in between. So the main functionality of the cluster manager is to basically take care of all the resources, to understand or to keep track of the resources that are there in the cluster, and then allocate the resources to the master node so that it can assign tasks to them. So like I said, your driver node is the master node of the cluster. So it is responsible for maintaining all the information about your Spark application. And so when you give it some code to run, it will basically analyze it, and it will distribute the work, and it will schedule the execution of the work across the cluster. So next thing in Spark is your cluster manager. Like I said, there are 3 different cluster managers that you can use with Spark. So one is Spark's standalone cluster manager, so which is what we'll be using in our local development. But if you're going to run your Spark cluster on cloud, if you're running it in AWS or Azure, we'll probably use something like Yarn or Mesos. Mesos is again another Apache project. And Yarn is Hadoop's cluster manager as well. So that's the cluster manager part. And now the executors. So the executors are the processes running on the worker nodes, and so they just carry out the work that is assigned to them, and they report the status of the work that is being executed back to the driver node, so that the driver node makes all of this information available to the users to see the progress of the computation. So now coming to Spark 2.x. So the first one was a generic Spark architecture. Now if you look specifically at Spark 2.x, there is not that much of a change. The high level architecture is the same, but the difference is here we have Spark session, which is like the entry point into your application. And so what we'll do is we'll basically submit our application to the driver node, and it will provide the Spark session to our application code, using which our application will be able to carry out or process various operations on the data that is distributed across the cluster. So we'll talk more about that. And so the user code that we'll submit to the Spark's driver, right, it can be written in a variety of languages. And so the reason is Spark's API are available in various programming languages. So you can write your application in Scala, you can write it in Java, Python, and even R. And so the reason Spark is able to support these many languages is because all your application code does is use this API, and Spark will internally convert all of this to Spark code and run the Spark code on the cluster. So that is why it is able to support so many different languages. And so yeah. And one more thing is Spark is written in Scala, so it is a JVM language, and so Java and Scala, they run within the JVM. So there's not much of overhead when you write your applications in Java or Scala. But when you're writing your applications in Python or R, the only difference is that your application code will be run as a separate process on the driver node. And so the driver node will somehow make this Spark session available to your process. And this can sometimes be an overhead, especially if you are using UDFs, which is written in Python or R. We will look at what UDFs are in the later part. But this is how it works. So when you write a non-JVM code.
Alfred, you have a question. Someone asked, what is Spark? Spark code.
So Spark code is nothing but something that you can think of it like your Java bytecode. It is something that runs on the Java virtual machine, right? Likewise, Spark code can run on the Spark computing cluster. So Spark translates that to your JVM code, and then it runs on your worker nodes. So, is that clear?
I have a question.
Yeah.
So what will be the load when we run a Python? Instead of writing a Scala program, you said like running a Python will cost kind of overhead.
So yeah. So this is the driver node. So if your application is in Python or R, right? So it will create a new process and it will run your code. And then whenever you're using the Spark session, it will go through the JVM, and then those instructions will be sent to the worker, and those operations will be carried out. There is another thing called as UDF. So we'll look at that later. So when you're using UDFs and when you're writing these functions in Python or R, right? That is when you will incur all those overheads. But
even when you write UDFs on Scala or Java, and you write it on, when you deploy it on a cluster, it will be slower. It's not that UDF functions are slower just because we are using Python or R.
But comparatively, if you write it in Java or Scala, the overhead will be less. I'm not saying that there won't be any overheads, but comparatively, it will be much less, because the way UDFs work is your function will be serialized, and then it will be sent to your worker nodes. That is the first step. And after that, right, if it is a JVM, if it is written in a JVM language, it will run on the JVM of the worker nodes. That is already spawned and it's running, right? Let's say suppose you write it in Python or R. So there is another step. Once the worker nodes get the serialized functions, they have to create another process to run your UDF, a Python process or an R process, and then for every row, when it is processing every row, it has to serialize the entire data, and it has to give it to that process. And after that gets evaluated, it has to get the result, and then again keep track of it in your JVM. So instead, if it was just running in your JVM, right, you wouldn't have this whole talking to another process, getting the result, right? So comparatively, your overheads are going to be lesser. Okay. So Spark session. Spark session is the entry point of any Spark application, and like you saw in the previous diagram, right? So whatever the user code, whatever operations the user code wants to carry out on the data, we have to use the Spark session to communicate all of those operations on the data to the worker nodes. So it is the entry point to Spark application. And so there is this one-to-one correspondence between a Spark session and a Spark application. So for every Spark application, you will have one Spark session. And so yeah. So now when we look at how the Spark's API is structured, we have the lower level APIs, which are RDDs and your distributed variables. And one level up, we have the data frames, data sets, and your SQL API. So this layer is like a high level API that Spark provides. And so specifically in Spark 2.x, the emphasis is on using these high level structured APIs than using the lower level RDDs. That does not mean that you should never use RDDs, but there are certain use cases for RDDs. But otherwise, if your data is structured, it has specific columns or specific types, then Spark emphasizes on using the high-level structured APIs. And so there are other libraries that will be used for streaming, like your structured streaming API and your Spark ML for machine learning and other advanced analytic stuff that are built on top of your high-level APIs. So you can basically use data frames for batch processing, for streaming, and for ML and all of that. So they're just built on top of that. So yeah, like I said, so these are your high-level structured APIs. So you have data frames, data sets, and your SQL. So before going any further, I would like to show a demo of how this all fits. So yeah, so to develop Spark applications locally, I'll show you the directory. This is my Spark installation, and so Spark provides you a bunch of tools that will help you develop your Spark application locally. And if you're writing your application in Python, then you would use pyspark. And there is also this Spark shell, which is nothing but a Scala REPL. You can launch it and you can just use your Scala code. And another tool is the Spark submit. Is basically if you have your application as a jar or as a zip or as Python files, you can submit. You can use Spark submit to submit your application to the Spark cluster and execute it. So right now I'm going to show you how to use pyspark. And so pyspark is again another REPL, but you can configure pyspark to be used within your Jupyter notebooks, and that makes this demo a little more easier to view. So I have configured that. I have configured my pyspark to I've integrated it with my Jupyter notebook, so I can execute my Spark code here. So like I said, your Spark session is the entry point to your Spark application. So in this step, what we are doing here is basically building our session instance that we can use in our application code. And for this demo, I'm going to be using a movies dataset. So we have movies, and we have the ratings for those movies. And so we'll be performing some processing over this dataset using Spark. So the movies dataset is a CSV file. And so to read the CSV file, I'm going to use the Spark session. And I'm going to specify a bunch of options. So I'm going to say that the CSV file, since it has a header, I'm going to say that it has header. And I'm also going to infer the schema. So this, when we specify this option, what Spark is going to do is it is going to guess the types of the different columns, and it is going to use that as the column types. And so finally, the format is CSV, and I'm going to load it. So this is comparatively a very small data set, because since it's a demo, I've used a smaller data set so that it'll finish quickly. And so now the data frame has been created from the CSV file. And to look at the schema of this data frame, we can just print the schema. And as you can see, it has 3 columns. So you have the movie ID column, which is of type integer, title, and genres. And so if you want to take a look at the size of this, so this is a very small data set. It's just 9,000 rows. So yeah, and that is how you read data frames. That is how you create data frames from a data set in Spark. So now you saw how we created data frames. I want to talk more about data frames. So you might have, if anybody has used pandas here, has anybody used? So you might be familiar with the concept of data frames, right? So the main difference between the data frames that are there in Pandas and R and the one that is available in Spark is that the Spark's data frame is distributed. So the data that we hold in Spark's data frame is distributed across your cluster. And so a data frame is nothing but it's just a table of rows and columns of data. And so the partitions or the way it is distributed, the data that is distributed, we call them as partitions. And each partition has its own set of rows and columns, and it exists on one physical machine in the cluster. And we'll look at how many partitions were created for the data frame that we created. And also, when we are using these higher level structured APIs, we don't really have to worry about these lower level partitions because they are all taken care of by Spark. So what I'm trying to do here is, now I'm trying to get the number of partitions that were created for this data set, and it's just one. The reason is, it is a comparatively small data set, and as you can see, it is just, it exists as one partition. But we can go ahead and modify this. Or even try to load a bigger data set and see how many partitions it creates. So I have one more data set which is bigger. Let me load this one. I'll show you. So this is a bigger data set, and like you can see, it's taking a while to give you back the results. And as you can see, now this is spread across 8 partitions, and so that's how Spark partitions it. Depending on the size of your data and the number of nodes you have and the memory that is available in each of these nodes, Spark partitions your data across the nodes in your cluster. So, okay, so now, yeah.
You said the number of partitions, right? Something like 8, right?
Yeah.
So you are running on a local host, whether
Correct.
it's communicating a remote system like remote systems, or you are partitioning those partitions in a single system, or you are connecting a remote.
No, right now I'm not using any remote cluster. I'm just running it on my local machine.
Particular machine, you partition into 8 segments. So
Correct. Spark has created 8 partitions in this one single node.
basically, if you have a gigabytes of RAM, so you are partitioning that into.
So this is not necessarily your RAM, but this.
So we need to configure.
So yeah, I'll show you that.
Here, command called repartition. You can get the number of partitions.
So I've commented it out over here. So that is basically what it does. So this repartition, right? So you can change the partition, but the whole point is you don't have to worry about all of these partitions when you're using your high-level structured API. Spark does that for you. Unless specifically you want to partition it by some column, so that you want to optimize some of the operations that are performing using that column, then maybe it makes sense. But otherwise, Spark takes care of all of that for you. Right? So yeah, so the core operations in Spark, there are two types of core operations. So one is called transformation and the other is called action. So the operations that we were doing, right, like reading the data set from a data source, that is a transformation. And so all these data structures that we are using in Spark, right, like data sets and data frames, they are all immutable. So which means when you are modifying them, you are basically creating another instance of that data set or data frame. So this, all the transformations result in a different data set or data frame, and since it is immutable, and you express all of your business logic in terms of transformations in Spark. And so again, there are two types of transformations. So one is called narrow transformations. Now that we know that all the data is partitioned and it exists as different chunks in the cluster, so what narrow transformations do is these are the operations in which when you operate on a partition, the result would be another partition, straight one more partition. And so if you have a bunch of narrow transformations, if you're performing a bunch of narrow transformations on the data set, what Spark does is it goes ahead and it pipelines them so that once one transformation or one of the transformation gets finished, so the next narrow transformation will be applied on the same partition and the output will be saved. So an example would be filtering data. So when you're filtering data, right, so your result would be another partition. It would directly correspond to one more partition. Whereas the other type is called wide transformations. And in this type of transformation, so there is no direct correspondence between one partition and the other. So after once this operation is applied on a partition, right, so the results will be shuffled across your cluster. So when you perform an operation on one partition, so you will not get a resulting partition directly from that. Instead, the result will be shuffled, and so your nodes will operate on those shuffled partitions, and then finally you will get a merged result. So an example for this would be sorting. So like we saw in the first example, so the first operation would be to sort the different chunks, and once that is sorted, right, the next step would be to merge it. And so when it is distributed, right, so your chunks will be in different nodes, and so to combine them you need to shuffle them, and you need to sort them by some value, key value pairs on each of the nodes, and then write the output to a resulting data set. So that is wide transformation. And so all of these transformations, right, so they don't get executed the moment you apply them on a data set or a data frame. So like we saw here in our example, right, so reading this was one transformation and it did not happen immediately. As you can see, it just finished quickly, and this would be the case even for bigger data sets. So what this means is Spark does not execute this immediately, it waits. And so this gives Spark a chance to optimize all of the transformations and build an execution plan before actually executing it. And that is why Spark is faster, because it is optimized. And it works like a compiler. It takes your transformations, it figures out the best possible way to execute them, and then it applies. So you may be wondering, so when does Spark begin executing all of this? Well, that happens when you apply another kind of operation called action. So all of this logical plan that Spark has built, right? So you can trigger it when you apply an action on it. And so there are 3 different kinds of actions. So one is like simply printing to your console. That triggers your execution. And the other is when you try to collect your data into some native collections in your programming language, that again triggers your execution. Or when you try to write it to an external data source, that also triggers an action. That also triggers your execution. So to show that, maybe let's try to, or maybe we'll come back to this later. Yeah. Okay, and so this brings us to, so whatever we have looked till now is completely Spark 2.x's API. So, and it is important to know the difference between Spark 1.x and Spark 2, because a lot of times when you're beginning with Spark, right, so when you're looking at some of the answers in Stack Overflow or reading some blogs, right, so it is, I think, necessary to differentiate between Spark 1 and Spark 2 code, because like I said, Spark 2, the emphasis on using the high-level APIs, whereas in Spark 1, right, so all your application code will be using RDDs, and they will use contexts as the entry point. So the first difference is in Spark 1, so instead of Spark session, the applications will be using Spark context as the entry to the application. And so this Spark context, there are different Spark contexts. So you have an SQL context, you have a context for batch processing. And so depending on which API that you are going to be using, you have to choose a Spark context for that. Whereas in Spark 2, you just have one unified Spark session. So you don't have to really worry about which API it supports. It supports everything. It's a wrapper around the different contexts, and it's one unified entry point into your application. So using it, you can, using the Spark session, you can do batch processing, you can use data frames, you can use SQL, and all of that. And the other major difference is they have changed the execution engine. In Spark 1, right, so they've been using something called as Volcano iterator model for execution. Whereas in Spark 2, they're using the Tungsten engine, which is like 10 to 20 times faster, because it works like a compiler, and it tries to optimize all of your transformations before actually executing them. So that is one major difference. Whereas in the Volcano model, that wasn't the case. And so the next thing is in Spark 1, right, you had different API for batch processing, and you had a different one for stream processing. Whereas in Spark 2, it's the same. So you can use the same high-level structured APIs for both stream and batch processing. And the other thing that has changed is spark.ml lib was the machine learning library that was used in Spark 1.x, whereas Spark.ml is the newer one. But one thing is Spark.ml still does not have all of the features that was provided by your Spark ML lib, but that is slowly changing, and new features are getting added. So yeah. So I really want to go over using SQL and a complete end-to-end example of using the Spark high-level APIs. So, like I said, the data set that we are going to use for this demo is basically movies data set. In one file, you have a list of movies with the name and the genre, and in the other file, you have the ratings for that movie. And so it has the movie ID, it has a user ID, and the user's ratings. So what we'll try to do in this demo is we'll try to find the average rating for a movie and the number of users that have rated the movie and combine it with the movie's data set so that we can see which movie has what rating and how many users have voted. So that will be a very that will be the example that we'll be looking. So I've already read my movie's data set, and as you can see, this is the schema of the movie's data frame, and it has 9,700 rows. Now let me read the ratings data set. I believe, no, I haven't changed it. So I'll use a smaller data set for this demo because it will run quickly. Otherwise, the bigger one takes a lot of time. And so this will be the schema of the ratings data set. As you can see, you have your user ID, you have the movie ID, rating, and the timestamp. So to perform the operations like grouping by your movie ID and then counting the number of users that have rated and your average rating, right? So we can use the data frames API as well. So you have all of these methods, all these APIs for data frame. But what we'll do instead is use SQL for getting or doing this processing. And so the reason why I would use SQL here is because I think a lot of us are familiar with SQL, and it is easier to write this. And so what Spark does is, after executing your SQL, it is going to give you back another data frame. So which is really helpful because that's what we are going to do now. And to do that, we need to create a view from the existing ratings data frame. And and the name of that view is ratings. So this will be like our table using which we can query it using SQL. And so in my resulting data set, I want to transform the ratings data set which has this schema. So I'll show you how that looks. So it looks something like this. And as you can see, for every user rating, you have one column. I mean, you have one row. What I want to do is I want to group it by the movie ID, and I want to count the number of users that have rated, and I want to take the average of all the user ratings. So to do that, I'm going to write an SQL query. So it's already there. So I'm selecting the movie ID, and then I want to count the number of users, which is basically your user ID, and I want to take the average of all the user ratings, and I want to round them to basically 2 decimal points. And so this is my view, and I'm grouping it by movie ID. So if I execute it, right, so it just finishes quickly. The reason is because it has not been evaluated. And so this will be the schema of the resulting data frame. And as you can see, after running the SQL, it has written me another data frame, which I can use like any other data frames. And this is the schema of that. And now what I'm going to do is I'm going to trigger the execution by performing an action. So show is an action. So this is when the whole execution begins. And since this is a very smaller data set, right, it finishes quickly. But for bigger ones, it will take some time. And so as you can see, it is grouped by movie ID, and it has found the number of users that have rated and the average rating. So these are just 2 rows.
Why do you think you never SQL over the data frames API?
So yes, that is very subjective. I mean, if you are very comfortable with SQL, right, then you would use SQL. But this functionality is also provided by your data frames API. You can still go ahead and like do the group by operation and aggregate it, sum, calculate the sum, and all of that using the data frames API. Like, yeah, it looks clunky, whereas this is, yeah, correct, exactly. And so now what I would like to do is basically take this resulting data set and I want to join it with my movies data set so that I can get one big data set of movies, user ratings, and the number of users that have rated. So we can do that by basically joining the two data frames. Spark data frame again supports joining operations, and the join that we are going to do here is an inner join, which is implicit in Spark, so I don't have to specify it. And the other thing that the join requires is an expression, which is basically I'm saying that from the movies data frame, I want the 0th column to equal the resulting average ratings data set's 0th column, which is basically movie ID. This can be done in a variety of ways. There's something called as call, which is a function that is provided by pyspark, and you can do something like this. Or you can just refer to the column by its index. So I'm now sticking with the index. And so once it is joined, I want to drop the movie ID column that is present in the average ratings data set. So yeah, let me show how this looks. And again, it's another transformation, and so it is not evaluated yet. And this will be the schema of the resulting data frame. So you have the movie ID and title, genres, and the number of users rated and the rating from the average ratings data set. And as you can see, since I've dropped the movie ID column from the average ratings data frame, so it is not present here. And so, yeah, I'll show you how this looks. So yeah, this will be our resulting data set, and so we'll do one more operation on top of this. So let's just go ahead and sort this data set by rating, and we'll do a descending order sort. To do that, I'm going to apply the sort operation, and I'm going to sort the column rating in descending order, and also the number of users column in descending order, and then I'm going to write it to the output folder.
So this not operation here, will itself take care of partitioning the data, like we do multiple cluster and not strip back?
Yeah. If you're using higher level structured APIs, everything will be taken care of by Spark. So you don't have to worry about the underlying partitions and all of that.
Another question I had is, does that if I, like in the previous line, use data frame dot join, right? So does this kind of operation have any performance, like improvement, better performance than using the spark.sql?
Yeah, that's a good question. So there is not going to be any performance difference between using your data frames API and your SQL. The reason being, Spark is going to convert all of your transformations, whether you specify it using the data frames API or SQL, into a logical plan, which is basically, and then execute that. So it's just your way of telling Spark what operations you want to do. Yeah, correct. And it doesn't make a difference.
Yeah, I have a question.
Yeah.
So we have, suppose you do some sort of operation and you get a data frame, right? For example, here, movie ratings data frame.
Yeah.
Does Spark keep that in memory if it's small enough, or for the further queries based on movie ratings, it will still go through the entire pipeline? Like it will
go through the part details, distribute it, and then fetch everything?
So correct me if I'm wrong. So what you're saying is this data set is going to be distributed. So your question is whether it would be in memory or how is Spark going to access that,
Once
right?
you have an intermediate data frame like movie ratings, the further step will it keep movie ratings in memory if it's small enough, or is it going to go through the entire thing?
So that depends on how the movie ratings data frame is distributed, right? So if it is there on a single machine, right, then it's no issues. It can fit in the memory, then it can keep it. Otherwise,
so movie rating is a data frame, right?
yeah,
So it will be like if it is big enough, then it will be partitioned into my
correct. And also, since you brought that up, Spark 2.x uses a lot of optimizations when it comes to memory. It not only uses your main memory, but it also uses the cache memory to speed things up. So if anything, if any data set that can fit inside a cache, if there is anything, so it will use the cache for that, and it will do all of the optimizations. So you don't have to worry about all of that. Yeah.
To add to that point, like what you asked, there is a specific function for like you can call the data frame name dot process. In that case, the data frame will be stored in the memory temporarily. So say like he has two tables to join here. Say table A is persisted, so that will be in the memory. Spark will take it in the memory. So it will, as he said, it will be in the cache. Further, you need to use this function called persist. Then now you do a join operation, it will be faster.
Just to mention one more thing, joining thing. So let's say one movie versus rating, right? So let's say movie is a smaller data frame, then and the rating is a very big data frame. Right?
Yeah.
So rating will be distributed across, whereas movie data frame doesn't need to be distributed. In that case, sometimes people use broadcast.
Yeah.
So,
Yeah, correct.
So in that case, every node in that cluster will have that in memory in that executable memory. So that way it will speed up the job. So that is also that.
Yeah,
First.
that's correct. So yeah, I've not included broadcast variables and accumulators in this slide, but like you said, right, if one of the data sets is like small enough, you can maybe optimize it more by broadcasting it to your worker nodes so that it can be kept in the memory and then like makes things much more faster. Thanks.
The points
Yeah.
Thank
you. Correct. Thank you guys. So yeah, and so right now, thanks. So the issue that we see here is because I already ran this operation and it generated an output folder. So this is a very common issue in Spark. So whenever you are writing it to some data source, right? If let's say for example in S3 or in HDFS, right? If that data folder already exists, right? Then Spark will throw an error. It will not overwrite it. So either you have to specify a different source, different destination, or you have to clear it out and then come and yeah. Correct. But by default, it will throw this error. So yeah, and like I said, it has generated it. And if you look at the output that is generated, right, you would see close to 200 files here. And any guess as to why this is happening?
200 part files.
Yeah.
Usually it should be the number of cores which you have when you run it locally. The number of part files that you get in the output should be equal to your number of cores.
That is not fully correct. It's number of partitions that you have. Let's say your database, data frame has one partition or 8 partitions, then and you perform a narrow transformation so that like each of this partition corresponds to one output partition. Then you would end up with 8 different files, 8 part files, right? Whereas the operation that we did, right, was sort, which is a shuffle operation. and by default the number of shuffle partitions in Spark is 200, and unless you change that, it's going to be 200, and you would get 200 files, which is basically 200 partitions. So just corresponds to 200 files. And yeah, so any questions till now?
I had one question.
Yeah.
So, like you told about the difference between Spark 1 and Spark 2, right?
Yeah.
So, suppose if someone has like legacy code in Spark 1, so
Mhm.
that it can be run in Spark 2, like is it backward compatible or like?
Yeah, it's backward compatible.
So,
All of the Spark context and all of the RDDs, right? They are still available in Spark 2, and you can perform all of that. The only thing is there are changes when it comes to streaming. The streaming API, right, has been unified, so the batching and streaming are the same. But other than that, if in the legacy code, if we are working with RDDs, if we are performing some mapping, some filtering, you can run it in Spark 2 as well, with or without some minor changes. Yeah.
The thing you said about the Spark engine, right? Lazy
Mhm.
evaluation
Yeah.
and the immutability, that is actually very similar to the Haskell, like the functional languages.
Correct. That's correct.
So is it for the multi-threading, since it is mostly because that
Yes.
was actually for the
Correct.
facilitating multi-threading, they have like everything is immutable and everything will be functions and
Yeah.
so is it for the, so everything since it is a multi-threading environment, they have decided like that.
Yes, that is absolutely correct.
So
yeah.
is Scala a functional language?
Yes, it is a functional language. And so, yes, you are absolutely right. It is very, helpful when it comes to processing in parallel. And the other thing is fault tolerance, right? So what Spark does is, when you begin the execution of all the transformations, it builds a plan. So it sends this plan to the worker nodes, and so each of the executors in the worker node, they would carry out this plan. So when one of the worker node goes down, right? So Spark knows what partitions or which data was there in the worker node, and now what it does is it's going to create a new node, and it's going to send over that data, and it's going to send the same plan. Now we can be sure that if you execute this plan, you would end up with whatever partition that the older node had produced. So they would be the same, right? So that way, being immutable helps Spark being fault tolerant.
I'm not clear with two things.
Mhm.
The last one is that
Mhm.
function programming and the 200 files that generated.
Yeah.
I'm confused with that.
Okay, so did you understand the wide and narrow transformations slide? You can go back to that. So did you really get what narrow transformations were? So our data is partitioned, and so our worker nodes are going to, or the executors, they're going to work on each of these partitions and perform some operation, right? So in the case of narrow transformations, what happens is it will process one partition, and your output would be directly another partition. And you don't need to send this partition over to other nodes in the cluster. So that's just the result. So if you have like, I don't know, maybe 10 nodes, and each of them have 10 partitions, right? So you would end up with 100 chunks of your output that are not shuffled, because it's just direct, like filtering, right? So you filter one partition, the max you can get is like one more partition or not at all, right? So it's just direct. Whereas when you perform operations like sorting, right, once you are done sorting one chunk, you need to shuffle it or send it to other nodes for it to compare with whatever chunk it was processing to get the final one, right? So when Spark does this shuffling, the final number of partitions it will assign is going to be 200 by default. You can change that depending on what operation you're doing and the number of resources you have. because if you have 200 partitions, right? So it's going to send this to, it is going to exchange it to 200 partitions. So each partition, after performing some operation on it, it's going to send it to 200 different partitions, right? So it can be an overhead because network operations, right? So you're going to send it. So if you want to avoid that, or let's say your cluster's network is not that fast, maybe you can reduce the number of shuffle partitions to maybe 100 or less than that, so that after performing some operation on a partition, the result has to be sent only to a fewer number of shuffled partitions.
So the partition you mentioned, 8 is different from the shuffle partition.
Correct.
Shuffle partition is default.
And the last
Yeah.
function.
Correct. Yeah.
Multiplay.
So where that began was because it was immutable. So do you want to add? Like, so he was asking me whether was it because if it was immutable, so that the parallel processing and all this multi-threaded application processing, you would end up with something that is consistent instead of many threads trying to modify the existing data set, right? You would not touch your existing data set. Instead, you would get a newer one, right? So even if something happens, if something goes wrong, correct. Yes. So you have your original copy as is, and you can always be sure that whenever you perform the same set of operations on the data set, the result will be the same.
But it only applies to scalar, which is a function programming, but it's not applied to Java, like that's not a function.
So to answer your question, see, Spark is written in Scala, right? So whatever you write is you are basically consuming Spark's API. So what that means is you are instructing Spark to perform some operation, which will basically get converted to Spark code, and it will run in the Scala. It will run as a Scala application, basically in the worker nodes.
Scala and Java, like they are
Yeah.
JVM based. So
Correct.
they run. In case of Python or like you said something different UF, I don't know.
UDF, right?
So
Yeah.
those get transferred to some sort of Spark kind of code. Is that?
So UDFs. So if you're talking about user code, right? So whatever I explained is what happens. So you use the API, convert it to Spark code. Whereas UDFs, right? They are simply functions. You can think of them as functions, right? And so what they're going to do is, given some input, they're going to give you some output, right? So Spark is going to use that function to transform your rows, to transform your columns. A lot of things, right? You want to, let's say, perform some operation on a column, right? What it's going to do is it's going to go over every row, pass the value of that column to a function that is running in as a separate Python process. So it will run in that Python process. The function will be executed. The result will be given back to Spark, and then it will proceed. It will create another data set. That is how immutability works when it comes to UDF. Is it clear? Good. So yeah. So since I think shuffle partition, I believe it's clear. There is one more partition configuration, which is called coalesce. So like I said, if you want to change the resulting number of partitions, or you want to combine the number of partitions that was created by Spark, you can use coalesce. So this will be very helpful when you're dealing with databases, especially when your destination is an RDS, is an RDBMS, right? So it has only a specific number of connections available for connecting with it, right? And let's say you have hundreds of executors that are trying to connect, right? You would obviously run out of connections, and that is going to cause an error. So in those cases, what you can do is basically combine your partitions from maybe reduce it from 100 to 10, so that you have 10 partitions distributed across 10 worker nodes, and only these 10 worker nodes will try to connect with your database, and so you won't run out of your connections. So this can be helpful at those times if you're facing such errors. And yeah, so like I said, UDFs are nothing but functions, custom functions that you can use in addition to other transformation that Spark provides you. So Spark provides you with a lot of transformations, like you can apply on your columns, but you want to go ahead and you want to create your own function, you want to transform it in a different way, right? So UDF is how you would do it. And like I said, you can write it in any language, but if you write it in a non-JVM language, you have that overhead of spawning another process in your worker node, serializing your data, passing to that. Instead, if it was just if it was written in another JVM language, it would run on the same JVM in the worker node, and there won't be that overhead. So you don't have to serialize your data, send it, like get it back, and all of that won't be there. So yeah, I think we're running out of time. So yeah, and finally, so I have whatever we saw in the notebook, right? So I have a file, and I've copied over that to this file, and it's the same. As you can see, I'm creating the session. The only difference is, so I am getting all of this from my arguments, so from my function arguments, and so to demonstrate running this on cloud, right? So we'll be using AWS EMR. So EMR is a managed service for running these frameworks like Apache, Hadoop, or Spark, Flink. And what it does is it's going to take care of creating the cluster using EC2 instances, setting up Spark, setting up the master node, setting up the worker node, and all of that. And so now all you have to do is basically submit your application to the master node so that it gets processed on the cluster. And there are various options that you can provide to create your cluster. You can specify the instance type that you want to use for your cluster. You can specify the number of instances that you want, and so on and so forth. There are a bunch of options. So I've gone ahead and I've created one cluster. So I've created this DevDay cluster, and so this runs Spark 2.3, and if you look at the hardware, I've used one node, or I've like created 3 instances. So 2 for my core worker nodes and 1 instance for my master node, and each of this is an M4 X large machine. And to submit or to run my application, I have to submit my code to the master node, and we can use Spark submit for that, like I showed you that earlier, right? So, and this I've SSH'd into that master node, and so this makes Spark submit available to me. And so these are the various options or flags that you can pass to your Spark submit. So, and I think in the interest of time, I'll just go over them very quickly. So in addition to your application code, right, and let's say you have some dependencies, you would pass the dependencies. You can pass the dependencies of jars, or you can pass their Maven repository package names, so that Spark downloads them and then makes it available for your code. And so you would also specify all your executor related configurations here. You will say how many executors you want and how many cores each of the executors should use, and the memory and all of that. You can specify that and you can run your code. So I've already copied my data to S3, and this is one more thing that EMR is helpful for. So if you have your data in S3, right, So EMR makes those files available to you as if they were in your local file system. So as you can see, I've just specified my S3 bucket names here. And and I'm specifying my cluster manager to be yarn. And I'm like requesting for 10 executors. And I'm specifying each executor should use 2 cores of CPU and 4 gigabytes of RAM. And this is just the application name. And so the deploy mode is cluster. So you don't need to specify this when you're running it locally, but when you're running it on a cluster, you need to specify this. And so finally, this is the application code. So since it is a Python code, I can directly give the Python file to it. And then, so these are all my arguments to my main function. So I'm passing in the movies dataset, and then the ratings dataset, and the output. And so now I've submitted it. It will take a while, but it would finally show up here in the application history for this cluster in EMR. And so this is the bucket that I specified. And so once it is finished doing the processing, it would output my files here in this bucket. Sorry, you're looking at the wrong place. Oh yeah, so the application was submitted, and you can see the history over here. And you can see all the executors that are allotted for this job. Okay. Yeah. And so the output is available. And as you can see, like how it was partitioned, that's the way it is also partitioned in the cluster. So, yeah, I think that's about it. Sure. Any questions? Yeah. So, any questions, guys?
If it is to be purely functional, I mean, if it is to be purely functional type, then there are some constraints, right? So how you would actually write a functional programming things. So given UDF that we submitted, did it actually be something like that, like no immutable things and those kind of things?
Yeah, you should.
Ask the constraints.
I mean, it has to be a pure function. Basically, it has to accept an output, and it has to give you back a result. And no matter how many times you call the function with the same input, it should be the same. So, I mean, it's just a simple function, right?
Yeah,
like,
I mean, it has different constraints, right? In a non-imperative languages, no, this one, like what functions. Since you mentioned Java, you could submit Java functions.
Yeah. So, I don't know how to put it, but see, there are certain types in Spark as well. So, like your string, integer, array, right? So, whatever your Spark code, I mean, whatever type that has been specified in your Spark code, right? So, they will be converted to the corresponding types in the language that you're using for the UDF, and they'll be more like your primitives. And not something complex. It supports arrays and structures, but otherwise,
But changing that, like changing the state of variables. I mean, Java would allow it.
So even if you change that particular argument that is being passed to you, right? What Spark does is it is going to create a new set. It is going to take this result and it is going to create a new data set or a data frame with that.
Use a function counterpart for that.
That's how it works. So it doesn't matter even if you try to mutate the object that is being passed to you, right? Spark is going to create a new data frame. And that is going to be immutable. No way it is going to change.